Hi. If you're watching this video, hopefully you're looking to get a little bit of Regents review while the New York State Chemistry Regents still exists the way that it does. Just a quick introduction, some best practices before we get started. The number one most important thing you can have available is right here. It's a QR code that's going to point you to the New York State Chemistry reference tables. It has all of the information that you will get when you take the test, and arguably a lot of the information you're going to need to take the test. Things otherwise you might want to have, some sort of a calculator handy, and if you need a paper copy or a digital copy of the Regents, there will be a link below. It is suggested that you take a look at these questions before you watch this video. It might move a little bit fast for some people, but hopefully you find this helpful, and let's get started. For those who need a bit of a review of what the Regents looks like, we'll be looking at the first half of Part A today. That's 30 multiple choice questions for the whole part. It's every unit you've seen over the course of the year. We are looking at more of definitions and concepts than calculation. We still do use the reference table, link above my head, but, not as many times we're going to be running to the back or grabbing our calculators. And depending on how you went through the year, these questions may be in chronological order that you learn them. The things in September will be question 1. Things in May or June will be question 30, but that's highly variable. So for the first question, these all are our models of the atom that I've shown here. We just have to match them up. Protons present in a nucleus, that's your Rutherford model. The Bohr model has your electrons being at fixed distances, these things called orbits. The atoms being hard or indivisible spheres, that's the Dalton model. And then down here we've got Schrödinger. So comparing all of those names to the models that we have over here, the one that has orbitals, there's this cloud going on the far right, that would be our wave mechanical model, so our answer here is 4. Second question, same picture, thanks to Compound Chem. We're going to look at our planetary model for these electrons. If we were to take an electron and move it to a higher energy level, or move it from a higher to a lower. That's what the question's looking at here. For this question, we're looking at moving from higher to lower, so that's this one here, and as you move closer to the nucleus, we've got positives and negatives attracting each other. As you bring them closer together, that's more stable. You are going to a lower energy state. This is a release of energy. We're not going to be gaining or losing electrons, so you can knock out the ion right away, but we're looking at releasing energy. Question 3. If you have something called an isotope of the same element, so there's a bit of a clue here since we're talking about the same element, that might be able to narrow you down to 2 choices even if you forget what an isotope is. The atomic number on the bottom left-hand corner of an element shows which element you are looking at. That is the number of protons. So if this is the same element, then you have to have the same number of protons. Knocks out 3 and 4 as potential answer choices. The only reasonable way you can get 2 different isotopes then is we have the atomic mass here, but for isotopes we're looking at our mass number being protons plus neutrons. Similar to atomic mass, it's the weighted average of the mass numbers that gives you the atomic mass, but in this case we're looking at the same number of protons, different number of neutrons. Those are isotopes. For question 4, now we have to look a little bit closer at this periodic table, so it's a really good idea to be familiar with what all this means. If we are in group 14, groups are labeled on the top, but they are the columns. And period 3, those are our rows. So group 14, period 3, we're looking right here. Our element is Si. Looking at our answer choices, they're not asking which element it is, they're asking what type of element it is. So this is a slightly different question. You do notice that there's this bolded line here on the right half of your periodic table. This is your border between metals and nonmetals. In between them we have our metalloids. Noble gases are found in group 18. So that's not what we're looking for because we're specifically told to look at group 14. In this case, group 14, period 3, our metalloids, there are 6 of them that you need to concern yourself with. And I've circled them right there. Aluminum is a metal. Polonium and astatine are radioactive. So some people say they're metalloids. Some people say they're radioactive. Their chemical properties are less important. But regardless, silicon is one of the ones I circled, and that is a metalloid. Question 5. Chemical properties that are most similar to potassium. Potassium, if you forget which elements or which symbols on the periodic table, table S does list many of them. Hopefully over the course of the year you've gotten familiar with a couple of these, Na being sodium and K being potassium. The ones that are based off of some other naming scheme, Greek or Latin, where the element was named a long time ago, so we took the symbol, but it doesn't line up with what we call it in English today. Regardless, the most similar chemical properties are going to come down to number of valence electrons. And that's the last number that you see here on your periodic table. And notice that these all end in 1, so they're all going to have similar chemical properties. So now you're just picking which one is also found in group 1. Chemical properties that are most similar, that's your code for same group. Which means now we're down to the only one that's there, cesium. There might be some others that are in the same period going across the row, but we're going to try and avoid that as a potential pitfall in our answers. Number 6 asks about a definition. So the least amount of energy to remove the most loosely held electron from a gaseous atom in the ground state. This is one big definition of the term ionization energy. There are a couple ways to approach this problem. The easiest for you, probably the most time consuming, would be to look at table S again. It lists your ionization energies. So we just have to look at the 4 elements in question. The least amount of energy is going to be the lowest first ionization energy. Our answer is sodium. Now, if you want to think about this another way, the periodic table does give you a lot of information. If you notice, all 4 of these elements are in period 3, which I've copied below, and the ionization energy seems to go up as you go from left to right. So this is high, and this is low. In this case, a low number is a least amount of energy. So another way to look at this would be to say which element is found on the left side of its period. When you're talking about different categories of chemical compounds, there are 3 real big ones we want to concern ourselves with. Ionic, covalent, and metallic. Now, metallic compounds aren't really compounds. I think I put the air quotes on the wrong thing. But here you're talking about a single metal like, say, sodium in the last problem, or some sort of alloy that's a bunch of elements put together. But regardless, they'll work the same way, but we're not worrying about that. Those aren't even choices here. So ionic and covalent are their only categories. If you're concerned with what molecular and empirical might be, in case you were concerned those might be potential answers, molecular is the actual number of elements found in your molecule, and that's code for a covalent compound. A good example of that would be, say, glucose with your C6H12O6. You've got a lot of particles all jammed together in that molecule. The empirical formula is the reduced ratio of the elements in that compound. For a covalent compound, you can turn a molecular compound into an empirical compound, or formula, might be a better word, by reducing that ratio, which in this case would be CH2O. All ionic formulas are empirical, and you can write empirical for covalent. So you could put molecular or empirical as subsets. So to go back and answer our question, we're looking for the one that says, covalent and ionic would be best. But since the word molecule does imply covalent, I think it's a hidden answer here. So our answer here is going to be 3. So we've got 2 atoms of fluorine become a molecule of fluorine. So let's quick draw our Lewis structures. And one of the things that really isn't shown super well in a Lewis structure is that our nucleus is positive, and then all of these electrons are negative. And that's our guiding force behind why bonding occurs. So as these 2 elements come together to form a molecule, you have a situation where there was all of these negative and positive charges further apart, and now they've come together. The reason they come together is due to that attraction. The other reason they come together from an energy standpoint is stability. And the real big thing for you to keep in mind here is that stability and energy are opposites. So if for some reason you make something more stable, that's a lower energy. And if you go from high energy to low energy, you've released energy. And if you go from low energy to high energy, you've absorbed. So let's put all that together and see what's going on here. So at the very least, I can be sure that a bond is formed as 2 atoms become a molecule. So we're going to get rid of 1 and 3 really quick because those are breaking bonds. So the question is, does forming the bond release energy or absorb energy? So again, stability being our standpoint, as you bond, you become more stable. Those attractions are allowed to work, and you make something that's more stable at a lower energy, so energy is released. Another quick way to think about that is that to get them unbonded, they're attracted, you're going to have to put a lot of energy into the molecule to force them apart. So if getting them apart would be absorption, then having them come together would be released, because that's the opposite. Which part of a calcium ion in the ground state is represented by the dots in the Lewis dot structure? So we've got our electron configuration there. So we're talking about electron dot diagram. I figure electron and electron, that would be a good place to look on your periodic table. And here we've got the symbol for calcium. So I see that our electron configuration is 2882. For the Lewis dot diagram, we are always showing the element symbol, which counts for all of the protons and neutrons in the nucleus and all of the inner electrons, and then we're going to put 2 dots. Why 2? We're only showing the outermost energy level of any atom. If it was carbon, we'd be showing 4 dots. So really the dots in the Lewis dot diagram are showing the outermost electrons, which in this case is the 4th shell of calcium. While it's true that there's also 2 electrons in the first shell, different elements would have a different number of dots in the 1st and 4th shells, or the 1st and 3rd shells, whichever is your outermost. So be careful, that's a distractor answer. Don't go for that one. While it's true, it's not like correct. Based on table S, an atom of which element has the strongest attraction for electrons? They're hitting us hard with these periodic table questions. This is electronegativity. I'm going to abbreviate, EN, found right here. Table S, strongest attraction for electrons and chemicals. So we've got aluminum all the way going to sulfur. Here we've got aluminum. Oh, we've got magnesium too. And chlorine. Aluminum to sulfur. But all 4 of these are found in the same period again. So I didn't copy over the image, but as we're moving from the left to the right, from sodium all the way over to chlorine, I guess in this case we could say argon. We're not going to for electronegativity reasons. I'm going to skip that for now. But we can see in general that the number is going up. So we've got low and high. It's the same trend as your ionization energy for a similar reason. But here we have our smaller atoms on the right side. Chlorine is smaller than sodium. The electrons are pulled more tightly by those extra protons in the nucleus. So it's harder. More energy must be expended to get electrons out, but also pulling on electrons, strongest attraction for electrons, will also be very high. So here our answer is going to be chlorine. Which substance cannot be broken down by chemical means? This is another definition. This is code for element. So that might not be insanely obvious from looking at these 4 answer choices, but we're looking for which one is the element. A couple ways to do that. One would be to look at your periodic table if you know all the symbols. They didn't give you symbols here, they gave you words, so you might need table S to look up a few of them. But I do see that there are some similarities here between 1 and 3 and 2 and 4. The ammonium and the ammonia seem to be coming in, and aluminum seem to be coming in. An element cannot be broken down by chemical means, and so how do you identify an element? Well, at the very least, we're looking for one word in the chemical name. As soon as you see multiple words, we know we're dealing with a compound. We're a little bit tricky here because the ammonia and the ammonium, that sounds like something that you've built a compound out of, but ammonia is not found on the periodic table. It's itself a formula. Ammonium is the conjugate acid of ammonia. It's a polyatomic ion, so ammonium chloride would be NH4Cl. Aluminum oxide is, of course, a compound, but aluminum, found on the periodic table, number 13, is an element. Kinetic molecular theory. This is one of those long list of things that you do have to kind of just know. I went to NASA's website and found some information for you about gases and how they work. You can read through those, but if you don't have them in your head, that's something great to put on some index cards and practice with that. But we're just now looking for which one lines up with what we're seeing on the left and on the right. So there are attractive forces. I don't see anything about attractive forces. Circular paths, constant random motion. But if I look at the image, these do not look circular, so I'm going to cross that out. Collisions reduce the energy. Frequent collisions, orders super, and the volume of the gas particles is negligible to the total volume of the gas. So these two, 1 and 3, are connected. If there were attractive forces, then the collisions would maybe reduce the total energy of the gas. You can kind of imagine if a bunch of magnets were to pass by each other, eventually they might stick. And that's not what we want to have happen with our gas because, well, if that happened, then things wouldn't stay gases, they'd become liquids. So I think both of those have to be out. Here, we're getting rid of. We don't want gases to, an ideal gas particularly, to have attraction. The perfect gas, no attraction. Collisions have to be elastic, which is the opposite of what's here. So the total volume of the gas particles is negligible compared with the volume of the gas, and you can kind of see that here. The particles themselves, if we squish them all into a corner, would represent a very small fraction of the overall volume of your gas. You might think there's a calculation here, but there isn't, but I'll show you how to figure it out if there was. What is the amount of heat released by 1 gram of liquid water at 0 degrees Celsius when it changes to 1 gram of ice at 0 degrees Celsius? So we're going from H2O liquid to H2O solid. As soon as you see the word heat, you should be looking in one of two places, maybe both. Table S, heat formulas, right there. Table B, constants, because we're talking about water. And most of the questions you're going to see here are about water, unless they're going to give you way more information. If we're turning liquid into solid, and we are at 0 degrees Celsius and 0 degrees Celsius, we're not dealing with this equation because delta T is change in temperature. So I also know that we're not dealing with the specific heat capacity because that's letter C and we're not using that formula. So the question here is, are we talking about heat of fusion or heat of vaporization? The word fusion means a transition from solid to liquid or liquid to solid. And the word vaporization is for liquid to gas or gas to liquid. So in this case, we're looking at the heat of fusion based on the question, which is 334. So our answer is 3. For question 14, this is one of those, again, you kind of have to know. Now, intermolecular force, some things that might jog your memory. Molecular, we just talked about, that means covalent, but intermolecular is between, not within. So covalent bonding is when two elements are sharing electrons. This is an intramolecular force, but that's not what we want here. Ionic bonding, well, that wouldn't fit with molecular because that's covalent, and metallic, again, is not covalent. So that does reduce us to hydrogen bonding. In case you want a brief review, we've got 3 different intermolecular forces. Hydrogen bonding, which is found in certain covalent molecules that have an HO, an HN, or an HF bond. In there, it's superpolar, it's super strong. Dipole, that's any polar molecule other than the ones I just mentioned. That is there in those, but it's not the predominant strongest force. And then dispersion forces are your weak, temporary, instantaneous dipole that is responsible for holding nonpolar molecules together. Dispersion's present in the other two, but again, it's that minor contributor. Which statement describes a reaction equilibrium? Well, concentrations are constant and rates are equal. So we're just looking for whichever answer gives that sort of information. The mass must be equal. Nope, that's close to concentrations. Entropy has nothing to do with it. The rate of formation of the products must equal to rate of formation of reactants. The number of moles of the reactants must equal the moles of products. So mass and moles, this stuff, they're both related. They're not equal, but they're implying the same thing. It's amount. They have to be constant, not equal. So that leaves us with our answer of 3. Hope this has clarified some things for you. Thanks for watching.